Welcome back, everyone. Today, the discussion topic is reactive distillation. I am Muhammad Saif, a chemical process engineer. So, I will show you how you can simulate your reactive distillation problem in DWSIM. After watching this video, you will be able to set up chemical reaction kinetics in distillation column in DWSIM. You will able to specify reaction chamber inside the distillation column, and finally you will learn how to recover unreacted reactant and recycle it, and the use of pump and valve unit operation in DWSIM. So these are the learning objectives of today's discussion. And first of all, let's have some basic information regarding reactive distillation. Actually, it is a technique in which chemical reaction and distillation happens in a single apparatus, and this technique is very useful for reversible and liquid phase reaction. For them, equilibrium conversion is very low. For example, if A reacts B and then product C and D forms, but after a little amount of C and D, they start to react again and form back A and B. So the overall conversion of the products is very low. So this kind of reaction, if we remove one of the product continuously from the reacting system, then according to the Le Chatelier principle, reaction will continue to the forward direction and more product will be formed. So this is actually one of the basic principle behind the reactive distillation. The standard solution of this kind of problem is you have to install a separate reactor and then install a complete distillation column to recover the unreacted reactants and send back for a reaction to increase the overall conversion of the reaction. But if you use simple reactive distillation for this kind of reactions, then you can integrate reaction zone inside the distillation column, where not only the reaction will happen but the product will also be separated side by side. So there are number of advantages of reactive distillation technique over the standard solutions for this kind of reacting system. Number one, it will simply reduce the capital cost. Also, it will lower the significant energy requirements, and obviously it will surpass the equilibrium limitation for the reaction, and also it simplify this complex process and increase the product selectivity as well as improve the separation efficiency. So for today's problem, for today's discussion, I have selected one problem from the research article, and I am citing the reference of that article is here. So I took the reaction kinetics from this article, and the reaction that today we are going to discuss is uh, propylene carbonate reacts with methyl alcohol and form dimethyl carbonate and propylene glycol. So this is the overall chemical reaction, and the rate of reaction for this reaction, I took it from this research article. So if you are interested to read in detail, just go to this article and read it. In this way you will learn a lot. So similarly, the forward rate coefficient and reverse rate coefficient, they are explained by these two equations, and the equation type is very similar with this form, and we need these coefficients to define reactions in DWSIM. So that's why I write the equation form here. So the coefficient A is 0 for the both forward and reverse reaction, and coefficient B is this one, these numbers you can see here, and the coefficient C is this number, but there should not be gas constant. So I just have to divide it this number with divide by the gas coefficient value, that is 8.314 joule per mole per Kelvin, and then you will have the coefficient C value, and the coefficient D is the temperature exponent, that is 1 in both cases. Okay, so we have this reaction kinetics for our today's reaction. Now let's move to the flow sheet that we will construct in DWSIM, and the flow sheet consisting of two distillation column. One is the reactive distillation column, the second column is a high pressure distillation column. In reactive distillation column, total number of stages are 46, and it is the column operates at 1 bar. There are two feed streams. The first stream is a mixture of methanol and propylene carbonate, and the second stream is pure methanol, and the third stream is the recycle stream, which will mainly consist of methyl alcohol. From top, dimethyl carbonate will remove, and the bottom mainly consisting of the second product, that was propylene glycol, and we have to find out the amount of dimethyl carbonate in the distillate of first hour as well as in the distillate of second hour. So this is the problem statement that we are going to solve in DWSIM. Let's go to the DWSIM software. So we are in DWSIM software. Now just create a new steady state simulation. So the first step is we have to specify the component. The first component is methanol. So the other one is propylene carbonate and propylene glycol, and the last one is dimethyl carbonate. Next step is to choose the thermodynamic property package. For this problem we will use UNIFAC in order to compare our result with the literature one. So next step is to select the units. So I am choosing C5 and then finish. Now we are ready to construct our flow sheet. Just select material stream. Okay, so there are two feed streams and one recycle stream. So just rotate this one. Okay, so the stream one, I am just giving name it methyl alcohol, and if you go here, so the amount is 630 kg per hour. So define here 630 kg, and in composition just click 1 and set all other zeros and accept changes. Okay, so it is at 1 bar and 630 kg per hour, 25 degrees C. The second stream consisting of propylene carbonate at the flow rate of 2508 kg per hour. So 25 kg per hour, and here just specify methanol is 0, propylene carbonate is 1, and the rest are zeros. Accept changes, and this one is feed 2, okay, and the feed 2 is consisting of pure methanol, that is 1425 kg per hour. 1425 kg mole per hour, and again specify the mole fraction for this stream as well. After that, just press accept changes, okay, and this stream is just rotate it at 180 degree and rename it like recycle stream, okay, and we are not going to specify this stream at the moment. Okay, so this one was propylene carbonate. Now the next step is just select a mixture and connect the methanol and propylene carbonate, and the introduce the outlet stream, and I am saying that this is F1, okay. So now we are ready to install our first distillation column, that is actually the reactive distillation column. For that, just go to the cape, open unit operation and install it, okay. So the total number of stages for the reactive distillation column is 46, and the feeds are entering at 5, 16 and 45. Click on it, open cape, open object editor. So the number of stages were 46, and the distillation is actually a complex distillation. Press OK. Okay, deselect this one. Now go to here. The operation is equilibrium column. Condenser is total liquid. Reboiler is total vapor product. And the feed streams are again 5, 16, 45. Okay, just 5, 16, 45. Okay, so we have defined feed streams, and then again just cross this one, select save the changes. Yes, you have to save them, and here I would recommend at this point just pause the flowsheet solver, because it will continuously try to recalculate at every time when you press any value, and it will slow down your process, okay. I will solve flowsheet in the end when I put all the input data, okay. I'm just disabling the flowsheet solver. Okay, now what is next? So the feed 1 is entering at stage 5. So at stage 5 we have to connect feed 1, and feed 2 is entering at stage number 45, and the recycle stream is entering at stage number 16, okay. After that, just go to the outlet and create top product and bottom product. So I am going to change their name. So this one is D1 and this one is B1. Okay, now I will finish the specification of reactive distillation column. So for that you have to again go back into the Cape Open object editor, and here we are. And now we have to define the thermodynamics. For this, Dekema, activity coefficient, unique vapor pressure, Antoine equation, and enthalpy will be the ideal one. And now the feeds are okay. Let's go to the reaction. So this is the new thing that you will learn particularly in this video. Okay, so how we can insert a chemical reaction in DWSIM in a distillation column. So these are the major steps. Okay, so let's start. Just click on this insert reaction. Our reaction is reversible reaction. Yes. What is the reaction type? It is a homogeneous reaction, and the kinetic basis is concentration. And the reaction zone, reaction start at stage number 5 and it ends at stage number 45. Okay. Now from overall chemical reaction, we have to specify the stoichiometric coefficient. For methanol is there were 2 mole, and for propylene carbonate it was -1, and for propylene glycol 1 mole, and the rest one is dimethyl carbonate 1. Okay, for product you have to enter stoichiometric coefficient as a positive number, and for reactant you have to specify them as a negative number. Okay, so this is done. Now there is another thing that has been asked, that is the forward orders stoichiometric coefficients and backward orders stoichiometric coefficient. For them, what you have to do, you just have to uh, go back here. So okay, so this is the rate of reaction coefficient that is based on the concentration. So with forward coefficient there are mainly two there are two mainly chemical species. That one is the propylene carbonate and methyl alcohol. Okay, and we have to specify them as there is no stoichiometric coefficient, so there is only one. So I will specify here PC, so it is 1, and the other one is sorry, 1, methanol is 1. Okay, for reverse for backward order coefficients, we have to put 1 as a positive for DMC and PG. So that is the PG1, and for methanol we have to put -1. Okay, and here we have to enter again 1. So by seeing this, I mean this is just the given data from the paper, just follow that. And for here reaction rate, the equation number, so just go to equation number 103. That is very similar with this equation that I already have written here. And similarly for backward reaction, the reaction type is again same, that is 100 and 103. Okay, so the coefficient A is 0 for both cases. Press enter. Coefficient B for uh, forward reaction is 16551.8. Press enter. And 19254.75. Press enter. And the C coefficient for forward reaction is 4976.36, and for backward reaction is 3402.15, and the coefficient D is 1 and 1, and the coefficient E, there is no E, so just put 0 0. And the stage volume, we are just taking assumption 10 cubic meter for per stage volume. You can take any number what you want, it's just the basis. So we finally successfully specify a chemical reaction here. Okay, so next step is just go to the pressures. Okay, and if you see here in flow sheet, you can see the top pressure is around 1 bar and the bottom pressure is 1.31 bar. So the top and bottom pressure we have to uh, choose from here, bottom and top pressure. The top pressure is 1 bar and the bottom pressure is 1.31. Sorry, it will be 13100 and the top pressure is again 0000. Okay, so the last thing that we have to specify for reactive distillation column is the top and bottom specification. For top, reflux ratio is given here. You can see for the first column is 0.87, and the bottom, for bottom, uh, the bottom molar product flow rate is given. So the bottom product flow rate in kmol per second, that is 0.01. Just press enter. Okay, now you can see all the ticks are already green except the result. So the first column is successfully specified. Just cross this one. Yes, you have to save all the modified changes. Okay, now the next step is the distillation D1 will enter into the second distillation column. For that, the second distillation column actually operates at high pressure, that is around 11 bar. So from 1 bar to 11 bar, so we have to add some pressure increasing equipment, pressure changing equipment, and the distillate is in the liquid form. We will install a pump. Okay, and the pump, the input of pump is D1, and we have to generate outlets. And what kind of calculation we need? We need outlet pressure, and the outlet pressure should be 11 bar and 75% efficiency of this pump. Okay, now the second distillation column is a high pressure column that also operates on a pressure difference from top to bottom. At top it's 11 bar and at bottom it's 11.3434 bar. So the total number of stages are 43 if we include the reboiler. Okay, so let's just specify this column as well. Click on it. Okay, and then introduce feed, that is the material stream number 8, and then press this outlet stream and create two outlet streams. So material stream number 10 is the bottom and material stream number 9 is the top. So I'm just saying it's a second distillate D2, and this one is bottom of second distillation column, that is B2. Okay, now we are going to specify the second distillation column. For that, just press on the escape open object editor again. Okay, so the second one is a simple distillation and total number of plates will be 43. Just write here 43. Okay, and press enter. Okay, so we are here now, and for second just go to the operations, and the reboiler is partial liquid product, we want its total vapor product, and the feed stage is 33. Just specify here 33. After that, specify the thermodynamics of this column, that is the decema, and the activity coefficient is based on UNIQUAC, vapor pressure based on Intwine, and enthalpy would be the ideal one. Okay, there is no reaction, thermodynamic properties it will taken from the database, feed is okay, go to the pressure section, and again the column operates at two different pressure, that is bottom and top pressure we have to specify. So the condenser pressure is 11 bar, that is 11 into 10 raised to power 6, sorry, 10 raised to power 6. Okay, and similarly control C, and the bottom one is 1.134 e power 6. Okay, so we have specified the pressure profile of a column. The next is just we have to specify the column specs. The top is already specified as reflux ratio, and the reflux ratio for the second column is 1.37, and the bottom product flow rate for the second one is 0.0068. Okay, now everything is specified for the second column. Just cross this one and save the changing. Okay, now what is left to complete this flow sheet? We have to install a valve, because the distillate is at high pressure. It will be around 11 bar, but the recycle stream will enter at the first distillation column at around 1 bar, so we have to decrease pressure, so we have to use this valve. Okay, so I'm going to give the inlet and outlet of this valve. So D2 is the inlet, and I'm going to create outlet. Okay, so just right click and invert horizontally, and similarly here right click and invert horizontally. Okay, now we have to specify the valve. So what we need from this, we need the outlet pressure from here should be 1 bar. Okay, it is 1 bar. Okay, now the last step to complete the simulation is to install a recycle stream. Okay, and then just connect material stream 11 and the outlet stream would be recycle stream, and invert horizontally. Delete this one, I accidentally create this stream. Okay, so before starting this simulation, yes, I would recommend that we have to put initial gas for recycle stream, because it will otherwise it will take a lot of time to converge. So this stream will mainly consist of methanol. So I am going to specify the composition 0 0 0 only methanol, and methanol moles sorry, molar flow rate should be 90 kg per mole. It's just the initial gas, you can put any number whatever you want. Okay, so now we are ready to solve this problem. Just activate the flowsheet solver and press F5 and wait to converge this simulation. And finally our flow sheet has been converged, but here I want to tell you one thing. I made a mistake during the pressure specification for second column. I just want to tell you, if you are going to follow this video, just click on it, go to Cape Open Object Editor and go to the pressures. And here if you notice that initially I insert 10 raised to power 7, that is actually becomes 110 bar. That is too much. We have to specify the top pressure 11 bar. Okay, I just correct it and rerun it, and the simulation runs successfully. Okay, so now and you also maybe notice that at the start I just give the gas value for recycle stream was 90 kg mole per hour. Okay, but here you can see when simulation is converged, the recycle stream molar flow rate is 456, and it is mainly consist of methanol, around 93 mole fraction of methanol. Okay, and what else we have to tell? We have to find the dimethyl carbonate in distillate and in bottom of second distillation column. So just click on D1 and here go to the compound amount. So you can have the amount of dimethyl carbonate in mole fraction, that is 0.11. but if you want to have a molar flow, just click on the results, and from results go to the instead of mole fraction, just click molar flows. So the dimethyl carbonate flow rate is 55, and similarly you can check the bottom of second distillation column. Okay, go to the results, and from results Just you can see in mole fraction, dimethyl carbonate is around 97%, and the molar flow is 23.81. So using these values, you can find the conversion of propylene carbonate, that is the limiting reactant for this problem, and it is more than 99.9% that the limiting reactant is converted into the our product of interest. So that is really nice. So I hope you understand how to simulate reactive distillation column in DWSIM. If you like this video and if you understand my content, so please don't forget to like my video and subscribe to my channel for more exciting videos like this. So up till next, stay tuned. Bye bye.